Gui.
molte altre più funzioni, però come una piccola introduzione al software può andare bene. E lasciamo passo a Gui.
Gracias.
Grazie a tutti.
Gracias, Ale.
Grazie a te Peppe.
Mm.
Merci Pepe, merci Alessandro, merci Fedele. So let's start. I will try to share my screen now. Yes, it's working. Share. Okay. Normally everybody see my presentation.
Yes, Gui, it's okay.
Perfect. So let's start. This is a case study of system alignment where I was working on the last summer. I will repeat a little bit some things that also Pepe explained it before. So it'll be a little bit some repetition as an introduction. So after choosing microphone placement, we are taking the measurement and collecting the impulse response data with the use of the exponential sine sweeps as the excitation signal. Because we are getting the impulse response data, we can work on it in the virtual DSP provided by Rita. Therefore, we can predict offline without making noise the different speaker alignment and the combination results. If we have different microphone position in the area, we can also do the spatial averages in just by sending one single exponential sine sweep. So all of this is possible by generating less noise. It's a must for now, I think, because as we know, for a live transfer function, we need to send high-level pink noise, and sometimes with a duration which is now for me no more acceptable. The level must surpasses the ambient noise, and the duration will depend on the experience of the user and mostly depend on the temporal averaging of the live transfer function engine. So this is difficult for everybody who is working on the place. We have rigger guys, we have lightning guys, video guys, and all of these people are working close to the PA system. And when we are generating pink noise, at a load level, it is not safe for them. It is difficult for them to communicate, and so that's it. We need a new possibility to gather some measurement. So as a summary, I think it's important for everybody to show the system designs that I worked on last summer to understand much better every measurement that I will show in Rita. So first of all, there is two different presets proposed by the manufacturer. I will show it as a ground plane measurement, and I will show also how Rita helped me to do the investigation on each different preset for make better choices for the next alignment procedure. We will also see the compatibility between the main PA and the low-end extension, which is hanged right next to the main PA that I will show in a minute. After that, we will do end fire alignment. And for finish, we will do the main and sub alignment, which is obviously the main and the end fire array alignment. So this is an overview of the system. So it was a metal festival, and as you see, it's raining, so we enjoyed a lot. It is a symmetrical system left and right. The brand deployed is a Coda audio system, which is very interesting brand. The main PA is a left and right line array system with a low-end extension on both sides. The subwoofer are in a left and right end fire configuration. There is also some fill system, in-fill and out-fill, and front fill for the first row and the sides of the audience. But we will not focus on this in this presentation. So as a more in-depth view of the system here, we have the main PA, which is 9 array model it's a line array element, three-way line array element, which needed B amplification. It has a very large bandwidth. The preset used here is the full DS FIR preset. This is a high latency preset. There is two different presets proposed by Coda Audio. This is a high latency preset and low latency preset. So what I will show now, this is the difference between them. So I will load my measurement, and by doing this way, it's like exactly taking two measurements, one measurement of the first preset and another measurement of the another preset. So this is only the main PA, only the nine line array elements. So first of all, we do not see the high frequency data. This is because we are using the FPPO technique, which is also commonly named as the constant Q transform, which is using different FFT size for each octaves. Since in Rita this is a post acquisition parameter, if I want to see my data, there is two solutions. I can synchronize my analyzer, or I can choose a full FFT size. And because this technique, FPPO technique, is very sensitive to time mismatching, to missynchronization, this is why we do not see the data. So I can choose full FFT size, and now we are seeing the full datas. Obviously, it's a little bit smoothed because by default, Rita always insert octave smoothing at 148. So it can be useful for people. So first of all, I want to also talk about this high frequency response jigginess. Actually, this is a ground plane measurement. So this ground plane measurement helped me to get rid of the floor bounce reflection. But this is not beautiful and flat concrete floor. This is a rough wasteland of a festival. So there is grass, holes, and stones. And actually, all of this are the size very close to the wavelength of this frequency, so it's interfering in my measurement. So the blue measurement, the first curve, is the high latency preset. The green is the low latency preset, and what is very interesting to see, it is exactly the same magnitude frequency response. But what we can see now, it's compare the impulse response. The low latency preset obviously arrive at my microphone position earlier, and the high latency preset obviously is later. There is a very obvious difference in the impulse response here. If I hide the blue one, I can see that this impulse response has less amplitude and has a very much longer. It is smeared in time because this is the normal preset, as I would call, and this one is the high latency preset, which I will show in a minute. The difference between them is the phase response. So I can use very cool feature in Rita, which is synchronize all. Actually, I use this feature for every field system alignment, for a front field alignment or out field alignment. What Rita will do actually when I click on synchronize all, it's to synchronize on the latest arrival and will delay automatically the earliest arrival measurements. And what is very handy here, it's actually Rita delayed my low latency preset measurement by 10.5 milliseconds, and this delay actually is kind of close to the latency generated by the high latency preset. The difference in these two presets, as we can see now, it's the phase response. In the high latency preset, we have a very linear phase response, and in the low latency preset, we have more phase shifts, so increased group delay as we go down to the lower frequency. This is the signature of the filters used in the preset, and this one is the phase linearization of the presets. So it has the advantages to improve the time domain fidelity by the expense of introducing delay in the system natively. So why I wanted to show you this, it's because we need to be aware of what we are measuring. We need to be aware of the preset of the loudspeaker that we are using. And as I explained, this preset is much better in improvement of fidelity, but it has already delay natively. So it is good to be aware of it because it's a specification which can help for doing the right choices in the later alignment procedure. So again, I will show last time the difference. One is a very linear phase response and the other one has more phase shift in the preset. So back to the slide. Next to the main PA, there is the low-end extension, which is the SC2 model. There is 4 SC2 by side. It's a simple 15 transducer in a bass reflex loading. The preset used is the omnidirectional, which is actually the standard preset of this loudspeaker. What is interesting with this SC2 model, it's a bass extension loudspeaker, and we can see that there is a very high overlapping range of frequency from 35 Hertz to 200 Hertz. It has many advantages. It is made to be deployed colloquially with the main PA. And the first advantage that we are using in this place, it's bring more low-end contour level and also increasing the bandwidth to a lower frequency of the main PA. Also, depending on the deployment, the advantages on increasing the directivity are also very useful with this loudspeaker. What we will see now, it's this speaker is made to be very close to the main PA, and it is fully phase compatible with the main PA. So it is already aligned. So I will show with Rita the verification of this. So I need to take the measurement of the main PA and I need to take the measurement of this low-end extension. So now I will synchronize on the main PA, Rita. So as we can see now, there is much difference in the measurement because now it's a microphone stand measurement. It's no more ground plane measurement, but it's roughly the same place where I choose to do my alignment of the main and sub. It's near the front of house position. And what we can see now, it's exactly the same thing as I said. It is a very high overlapping range of this low-end extension with the main PA. Which is very interesting because we can see also that the phase response are very, very, very close and very, very aligned. It also increased the bandwidth of the main PA by going lower. So actually now I can see that these two speakers, the main PA and the low-end extension, are fully compatible. Okay, there is a slight phase shift here, but it depends maybe on my microphone position or maybe on the floor bounce, or maybe it is natively like this. I'm not sure how to explain that very, very accurately, but it is less than 60 or maximum 90 degrees of phase offset between these two systems. So obviously the summation will be very great. So unfortunately, I do not kept the real acoustical summation because I took it as a snapshot, and I always erase or delete the snapshot after use. So I just can show you the mathematical summation proposed by Rita, and as Pepe showed us, the mathematical summation is always in a good agreement with the acoustical summation. So we will see in a minute. So by activate the mathematical summation, we can clearly see that this system is natively aligned. It's deployed very next to the main PA. There is less than 2 meters. I try to put 1.7 meter between the main PA and this low-end extension. So we can consider it as one loudspeaker, and now we know that it is fully phase compatible and already aligned natively. So this is the list of my worries, and we can go on and continue the alignment procedure. So now we are talking about the end fire. So this is a 3-element end fire with 2 SCP model subwoofer per stack in the end fire. The SCP model is a double 18 inches in the bass reflex loading. It has the preset SCP Omni 70. For many reasons. First, there is another preset which is the Omni 100, but I will not use this preset because, as we know, there is a source separation between the main PA and the subwoofer on the ground. So because of this separation, we know that it introduces comb filtering, and that's why it needs to be aligned at well-choose microphone position. And so my philosophy in this kind of configuration is to use the main as low as possible. So we are well served with the air ray because it goes down until 50 Hertz, and use also the subs, the high frequency range of the sub as low as possible. So it goes until 70 Hertz. So this is in an attempt to reduce the lobing effect, which is that will occur in the vertical plane because of the source separation. So all of this design is really oriented to be, like as I love to say, designed to align. You know, so. Yeah, this is a 3-element subwoofer, and I will show you more in depth what happened here. So we have the first stacks of subwoofer next to the close to the stage, which is our reference, the T0, and the second one is the T1, and the third one is the T2, and all of these stacks are delayed to the first one. There is 1.2 meters from grill to grill of each subwoofer. This is the quarter wavelength of 70 Hertz. This is also because, as I showed before, I choose this Omni 70 preset. So by design, I choose to use the quarter wavelength of 70 Hertz. So if I translate this distance, 1.2 meter in delay at 21 degrees, it must be 3.5 milliseconds of delay. But we will see that the theory and the reality are always a little bit different. So I will load my 3 measurements. I took this measurement also at the same place that I will do the main and sub alignments. It's maybe 25 meters far from the stage in the on-axis of the end fire array. So I will load this impulse response. So what we can see here, we have the 3 measurement of the 3 stacks. So what happened on the frequency region? Sometimes it's damaged frequency response. It's due to the subwoofer cabinet size because they are acting as an obstacle between each other, and the high frequency range is also disturbed by the size of the subwoofer. There is a diffraction occur, and also some reflection between the cabinet because of the size of it. What is very interesting with Rita, it's that because of the technology and the technique used for capturing the impulse response, we have very high quality impulse response of subwoofer. And now we can clearly see that the first arrival is the closest to the microphone, is my T2 subwoofer, the first one, and the second one is the green one, is the T1 just behind it, and our reference is the blue, the T0. So with Rita, no matter in the order that you will take your measurements, normally with the live transfer function, we love to take our reference in first, but with this kind of measurement techniques, no matter which measurement will come first, since you are not moving your microphone position, I can start by taking the T2, the T1, or the T0, or in every sense that we want, because we can clearly see that the impulse response already explain all the story. So what I love also to verify in the field, it's that physics is working. So another thing that is very interesting with Rita, it's since we have a high quality of impulse response in the subwoofer range, I can synchronize Rita on the maximum linear amplitude peak of the impulse response of my reference subwoofer. So if I click on synchronize, here we are. Now Rita is synchronized on my first measurement, on my T0. And what I love to verify in the field, it's since I chose a quarter wavelength of 70 Hertz between cabinets, between grill to grill, I love to verify that around 70 Hertz, yes, physics is working. We can see that we have two division, and two division in Rita depend on the presets that you are, the parameters that you are choosing. It's 90 degrees of phase shift, so of phase offset between the cabinets. So physics is working, it's good. We have what we are looking for. So as we know, 1.2 meter, if I translate this distance in time because of the sound speed at around 21 degrees, it should be something like 3.5 milliseconds. But what we can see, it's maybe not sufficient. Many reasons for that, because the size of the cabinet, because of the diffraction. So we can tweak a little bit this delay, and I ended up with 4 milliseconds. And now we can clearly see that the phase response are matching and the impulse response are totally matching in a good agreement. So I would be also attempt to just insert the double, so 8 milliseconds to this subwoofer, to the third one. So 8 milliseconds, but it seems also to be not enough. So I ended up with something like 8.3 milliseconds. Okay, now our impulse response are totally aligned, and what it is very cool with Rita, it's since we can do the summation in silence, we can verify that our alignment is working. So it is very, very convenient and handy. We have the summation impulse response and the summation magnitude response. So I will take this and will save it in a snapshot. We'll stop the summation. Okay, I have my summation here. I will show now the difference between the summation proposed by Rita, the mathematical complex summation, and the real acoustical summation that I did in the field. And obviously, it's in a real, really good agreement. So this is very, very cool features to have the possibility to do the mathematical summation virtually inside Rita, and after that verify in the field that our measurement is working and our alignment is working also. So now that this end fire is well aligned, we can continue by doing the main and sub alignments. So I will load this measurement. So now we know that the end fire is working, so we can consider this end fire array as one and only loudspeaker element if we want. So I will synchronize Rita on the main PA, as I love to do usually, because it's my convention, but we can also have the possibility to have the subwoofer point of view. So if I want, I can synchronized on the point of view of the subwoofer. It's the same story, but for some obvious reason, I involved with before to be synchronized on the main PA as a reference. So we can see at around 100 hertz, there is 180 degrees of phase offset, which is, as we know, this is half a period of 100 hertz, which is 5 milliseconds. So this subwoofer array needs 5 milliseconds. And now my subwoofer array is aligned to my main PA. I will do the summation. Okay, the summation is very great. I can keep, again, this summation for further investigation later. I will change this color. Choose another color, like pink, for example. Okay. I will go out from the summation mode. And now, okay, I took this snapshot. I will hide it for a moment. What we have here, one can come and say maybe that, okay, we are well aligned, the summation is great, but if I'm looking to the phase response, maybe the subwoofer needs more delay because we are not totally matching in the lowest frequency range. And I say, okay, we can try. We can clearly see that around 70 hertz, we are aligned. So, or I can add full period of 70 hertz to my existing delay in Rita, or it will be obviously too much, like 14 milliseconds, it will be too much. So it will be around 19 milliseconds. It's too much delay. So what I can propose is to add, to stay aligned at this frequency, 70 hertz, it's to add half a period of 70 hertz in a combination with polarity reversal. So if I add a half a period, it's around 7. It's 12 milliseconds of delay in combination with polarity reversal. And also I can tweak a little bit this delay to get better matching in the lowest frequency region. So now we have a very, very good phase response matching on the lowest frequency range. So I can take, again, this summation. Okay, but already we can see that we have not the best summation as we would deserve in this frequency range, but I will keep it as a snapshot for further comparison. I will go out from the summation mode. There is 2 reasons for why I will not choose this alignment preset. First of all, I have less summation as I have already. I have less level in the summation that I have natively with my main speaker. So already I know that this is not the right choice for my alignment. Also, there is a need for polarity inversion in this alignment. And this polarity reversal goes against the philosophy of Coda Audio brand. This manufacturer do not advise anybody to use polarity reversal in any loudspeaker alignment because their loudspeaker are already phase matching, already phase align natively. So we do not have to use polarity inversion in their loudspeaker. So by knowing all of this, I still can compare my snapshots of the first alignment and the second one. I can also choose another color, maybe green. Okay. So obviously we can see that the pink first alignment is much more interesting than the green alignment for obvious reason, because the green alignment need a polarity reversal, which goes against the philosophy of the manufacturer. And also there is not so good summation as the first one. So I will back with my first alignment, which is take out the polarity reversal and use 5 milliseconds of delay. And now, okay, we know that by the summation that I took before, we have the pink summation, and I will compare with the real acoustical summation that I did in the field. I will resynchronize everything. Okay. The real acoustical summation is in a very, very good agreement, again, with the mathematical summation proposed by Rita. And this is very convenient to have the mathematical summation and to verify it on the field if everything is working well. So that's it for me. I hope you enjoyed this presentation. So, Fedele, I will stop
Okay,
my
Gui.
screen.
Thanks, Gui. Great presentation. Beautiful, consistent, great presentation. Thanks. È magnifica la presentazione di Gui, perché ci dimostra come effettivamente si può essere non schiavi delle schermate, dei software, ma possiamo rendere questi ultimi strumenti utili al nostro servizio, al servizio del nostro intuito, della nostra esperienza. Mi è piaciuto molto quando ha detto, no? Il corretto e teorico allineamento tra main e sub richiederebbe un'inversione di polarità e un ritardo differente da quello che poi in realtà come soluzione il ritardo ho preferito introdurre. Perché? Perché semplicemente il gioco di overlappare le tracce di fase sullo schermo non mi soddisfaceva completamente. La soluzione che più mi garbava, no, all'ascolto era quella di un approccio più critico, di un differente delay senza l'inversione della polarità. Bene, mi piace questo approccio al sound system tuning perché dimostra, diciamo, un approccio coerente con la realtà, coerente con l'ascolto. Se per voi è tutto, ricordo ancora l'importanza dunque dell'ascolto, dobbiamo rieducarci all'ascolto. L'importanza della Room Impulse Response. Ogni stanza, vi ricordo, ha la sua specifica Room Impulse Response. Ogni posizione della stessa sala ha la sua specifica Room Impulse Response. Noi con la trasformata di Fourier trasformiamo, come diceva Pepe, no? Questa informazione nel dominio del tempo in una informazione nel dominio della frequenza fatta di una schermata di magnitudo e in una schermata di fase. Ma come ad esempio insegno nei miei corsi, nell'analyzer, anche se decidiamo di guardare da una traccia di magnitudo e fase, tenetela sempre bene sovraimpressione l'immagine della live impulse response di quello che state facendo. Ricordate la risposta all'impulso della sala, che possiamo poi elaborare anche successivamente, abbiamo visto comodamente da casa, è l'impronta acustica della sala. Io andando in un nuovo teatro, visitando come site survey un qualsiasi ambiente in cui andrò a installare un progetto sonoro, no, per cui sono stato chiamato a lavorare, entro nella sala e la prima cosa che mi basta fare è battere le mani ed ascoltare. Educhiamoci all'ascolto, rieduchiamoci anzi meglio all'ascolto. Non perdiamo mai l'opportunità di ascoltare le sale in cui ci troviamo. In questo modo, con semplici strumenti noi riusciamo a catturare la risposta all'impulso di una sala, ok? Un semplice recorder, uno scoppio di un palloncino, di un clappatore, e abbiamo così a portata di mano nella nostra SIM card un file wave che rappresenta l'impronta acustica di quella sala, che possiamo editare, trasformare, e i modi per farlo poi ovviamente non è questa la sede per spiegare quali sono, ma ho qui dentro nel mio taschino, no, la stanza in cui devo andare a lavorare e a installare il mio sistema reale. Quindi grazie a tutti, grazie Gui, potete accendere i microfoni, open your microphone and open your videos. Pepe, you have something else to talk about?
No, por mí todo bien. Muchas gracias, Fedele. Fantástico, Gui, fantástica presentación. Gracias.
Thanks Pepe for your present. Sono veramente onorato di averti qui con noi. Grazie ad Alessandro, poi vado a riguardarmi quello che hai tradotto e come hai tradotto, magari faremo i conti più tardi. Ok, grazie a tutti, buona serata a tutti. Vi ricordo che troverete la registrazione perché qualcuno già l'ha chiesto in chat, troverete la registrazione del webinar sul mio canale YouTube. Buona serata a tutti, ciao!
Buonasera.
Ciao, buonasera, ciao.